Hello class, this is Mrs. Ayodeji with today's video on 11.7 The Logistic Model. We're going to be doing a lot of math in this video, so I strongly encourage you to take down notes, writing important vocabulary, formulas, equations, statements, and graphs in your notes. And at the conclusion of watching the video, again, you're feeling free to pause, replay, or rewind the video as often as you need. But at the conclusion, you're going to write a brief summary of what occurred in the video and submit that summary via the online WITS the night before class. All right, let's begin. So we've been dealing with differential equations and coming up with solutions if differential equations look of certain models. And to summarize, if the differential equation looks like this, dp dt is equal to some constant times p, then we know that the solution is going to be an exponential form, and it represents growth if k is greater than 0 and decay if k is less than 0. And we call this k being a continuous growth rate. We've also been solving problems that relate to Newton's law of heating and cooling, which we know that when we see a differential equation with representation of d sub t, in this case instead of p equals d sub t is equal to a constant times the difference between t and some constant, then our solution is going to look somewhat like that. And plus or minus will be depending if we're talking about heating or cooling. So today we're going to be talking about another model that looks very similar to the relative growth rate, continuous growth rate model, and that's called the logistic model. But before we begin, let's start with this continuous growth rate model of a differential equation. dp dt is equal to k times p. So let's solve for k, get k by itself. And because we know that k is a constant, if I were to graph 1 over p times dp dt versus p, I would get a straight line, as you can see right here. This is 1 over p dp dt versus p, and it's a straight line, a horizontal line where p is equal 1 over p dp dt is equal to k, which makes sense. And this is the exponential model. But what if p had some limits on it, and it could not just keep going on forever and ever and ever? And there is some value for which p, not k, some value p that p could not go above. So let's call that limiting value L. Well, what would happen to this model? Well, if we call this a logistic model, and it occurs as t goes to infinity that p approaches some L value. And if p approaches some L value, then dp dt is going to start getting closer and closer to 0. Well, why is that the case? Well, just think about this. If here's p increasing, whatever, increasing, but then it reaches some L, and this is my graph, then what's going to happen is it's not going to go past whatever line that L is. It's going to just, the rate of change is going to get smaller and smaller and smaller and closer to 0. So over here, 1 over p times dp dt ended up being constant, but with the logistic model, 1 over p dp dt is going to decrease in a linear fashion. And that linear fashion is what makes this a logistic model. So in the logistic model, we have 1 over p dp dt is equal to a linear line with negative slope, okay? And it actually reaches the x-axis, in this case the p-axis, when we have L, okay? At that point L, because that's our limiting value. So when our p-value actually gets to L, dp dt is going to be equal to 0. So this is why this value goes from up here all the way to down here. So let's talk about this logistic model. The logistic model looks very similar to the relative growth rate model that we had before, or continuous growth rate, depending on what constant you're looking at. But anyway, so 1 over p dp dt is going to involve k, but that k is not going to be the only thing that is involved in 1 over p dp dt. Like I said, that 1 over p dp dt will decrease in a linear fashion. And so the best way to represent that is in this linear equation with linear with respect to p. And the idea is when it's p is equal to 0, 1 over p dp dt will equal k. And when p is equal to L, that limiting value as we see up here, 1 over p dp dt will equal 0. And so we have this linear expression to represent that. And either of these ways is fine. Okay? Another way to represent that just to solve for dp dt is in this format. So if you see a differential equation in this format, a constant times your p, or your solution, times 1 minus p over some other constant, that lets you know that this is a logistic model. So please highlight that, square it, turn it all around. Okay, so now we're going to take a look at what does that information tell us. So over here we have a slope field for 1 over p, for dp dt. And we have an example of a solution. But I want to focus right now on our actual differential equation. And as you can see, this differential equation is really a quadratic function in terms of p, because I have kp times p over L, okay? And a quadratic function, since our kp squared has a negative in front, means that it's a opening down quadratic function. So let's take a look at that graph and see what it looks like. A couple things to note is that our quadratic function has zeros when p is equal to 0 and when p is equal to L, as you can see over here. And it makes sense, it's consistent with this equation as well too. But where is the dp dt graph highest? Well, it's highest at L over 2. And the reason why it's highest for L over 2 is if I were to take the second derivative of this function, I would get something that looks like, my second derivative down here, it's going to look like this with respect to p, and it's a linear function. And the linear function, as you can see, when p is equal to L over 2, we're going to end up with this being equal to 0, which makes sense because whenever the first derivative of a function is 0, it means that you have a local maximum or minimum. In this case, we have a local max. So L over 2 is when we have the highest rate of change for our solution function p. Well, why is that important? It helps explain the slope field. We can see that when p is in between 0 and L over 2, the slope of dp dt is positive and increasing, and when p is between L over 2 and L, the slope of dp dt is still positive, but it's decreasing as well. Okay, so we've seen what the graph looks like, but how do we get the actual solution or a general solution for a situation that has a logistic model? Well, as you recall, our dp dt looks like this, and we can rearrange it to look something like this as well. And we can take, again, using separation of variables, take this and take the derivative of both sides. Then using partial fractions, break that up, this fraction up into this form. And when we take the derivative of this, we get natural log of p minus natural log of L minus p is equal to kt plus c, using separation of variables. Doing some more lovely algebraic tricks and methods, we end up with something that looks like this. Again, I know some of you may be wondering, why is it plus or minus e to the negative c? Why isn't it just plus e to the c? Well, as you know, the exponential function is positive for any value t, in this case, whether it's positive or negative. But since we're taking the absolute value, then this answer could actually be negative. And the only way that this expression in here can be negative is if this constant is positive or negative. And so that's why we have that plus or minus there to cover our bases. So even though e to the negative c is always positive, we can put a negative in front of it so that we can cover our bases in case L minus p over p is a negative value. Okay, again, doing some more algebraic manipulations by replacing this constant with a. And then to figure out how to determine what a is, Again, let P equal P naught. Okay, so that's the initial value. That's when T is equal to 0. That's what our population is. And so then we end up with this expression when we substitute N for P. And so A can be found if we know the initial population and our limiting value. And basically A is essentially the ratio of the difference between the limiting value and the initial value by the initial value. So you should memorize that. Write it down somewhere, put a box around it, because that's going to be important. Another algebraic manipulation, since L minus P over P, i.e. our A times e to the negative kt, we can rewrite that as L over P minus 1. Then we can rewrite this expression over here as that. Move the 1 over to the other side. And then do some more algebraic manipulation, and we take this original logistic differential equation, which this is. Maybe you see something that looks like this. And then we can make a general solution to look something like this. Okay? And this is very important that you memorize, know like the back of your hand. And to, again, L is the limiting value. You must know that. And then to figure out A, again, it's the ratio that we talked about earlier. So highlight that, square it, put a big circle around it. You need to memorize all of this, okay? Now I'm going to end the video because it is over 11 minutes, but I will make another video that I will attach to it with examples of how we can use this logistic model. And it's really cool because it's talking about oil production and population. So I really encourage you to watch the accompanying video for that.